Yeah, good afternoon, everybody. We're just going to wait just 1 or 2 more minutes here before we get formally going with our Live from the Lab event. So I'm glad you can all join us. I see about a large number of attendees coming through here. So just give it 1 more minute and we'll make the formal start. Okay, see just a couple more coming in now, so it's slowing down. Okay, well, welcome everybody. Thank you very much for taking time today to attend our latest Live from the Laboratory here in Billerica, Massachusetts. My name is Vic Furzy. I look after sales for the Eastern region here in North America for our life science mass spectrometry products. So Bruker would like to welcome you also to our lab. As you see on the other video feed there, we have Matt Willits, who's really going to take the lion's share of the time today and present to us maximizing sequence coverage and data completeness with dia-PASEF and the timsTOF Pro 2. And this is all with a 4D bottom-up proteomics approach. This latest Live from the Lab follows on from a recent one where we did a data-dependent analysis approach with our real-time identification PASEF workflow. And what we're now going to do is DIA. So this is a different workflow. I think you're going to see some tremendous benefits and a real nice evolution of the technology here. We have some housekeeping things here. There is going to be a Q&A session via the chat. So if you can put your questions in the appropriate place there and send them to the organizer, we'll do a little session after the actual live demonstration component. In addition, we have 2 pieces of collateral information here. There's a poster showing this workflow that was recently presented at, I believe, at ASMS 2021, late in the year. And there is also our application note number 120, which also shows about looking into high complexity proteomes with this DIA approach. You can download those as you feel as you need to. Within the GoToMeeting environment, you can see the camera views on the top here, and then hopefully a data screen with a slide currently underneath that. There's a bar between. You can slide that up and down, and that will change the relative size of the video feed versus the actual data or display feed. And so there are times, you know, during the demo, you might want to zoom in on the actual video part, and then there's going to be others where you may want to concentrate and enlarge the actual data window size. So I just want to make you know that that's very easy to do. So I think without further ado, I'd like to now hand things over to Matt and welcome you directly from our laboratory environment here in Billerica. Thanks so much.
Cool. Thanks a lot, Vic. So yeah, hi everybody. Yeah, so as Vic says, we're here in our demo facility in Billerica, Massachusetts, and I'm going to take you through the acquisition of a complex cell lysate sample using our dia-PASEF workflow. So I've just put together just a little bit more detail on what I'm going to show you today. So I'm first of all just going to give you an overview of the setup we have and that we're going to use today. Then I'm going to start actually a live dia-PASEF acquisition. So I'll show you how we start a sample, you know, setting up the methods appropriately. We'll get a sample acquiring. While that sample is actually acquiring data live, we'll maybe dig into a bit more about how we have the system set up here in the lab, and maybe a bit more of a background on the TIMS, the trap time mobility capability that we have on the timsTOF, and how we apply that to DIA analysis and some of the benefits that that can provide. We'll then go on and process that data that we just acquired in the DIA-NN software. We'll also look at some software processed in Spectronaut, and then finally, as Vic says, we'll obviously take any of your questions you have that may arise during the presentation. Okay, so let's first of all just quickly take a look at the system that we have here set up in the lab this afternoon. So what you'll see is, I've just sort of zoomed in here so you can get a bit of a closer look. So we have our nano-elute, nano-HPLC system. So this is connected via our transfer line here to our column heater, where obviously we have our column. Today we're using an ion optics 25 centimeter column for the separation, which has an integrated emitter, which is interfaced directly then with our captive spray source, which then obviously ions enter into the Tims-TOF Pro 2 itself. And then we're going to analyze the peptides that come out of the column using our dia-PASEF workflow. Okay, so as I said, we can come back to that in a little bit just to discuss some more specifics there, which might be interesting. But maybe now we can actually just jump to the actual software itself, and we can actually set up an acquisition, and I can take you through that process. Okay, so first of all, so what I've got displayed now, what you can see now, and Vic, if you don't see this, please let me know. But
all good.
What you can, thank you very much. So what you can see now is our TIMS control software. So this is the bit where we set up our mass spec methods, right? And so I have one of our default methods for DIA analysis of short gradients. So I'm going to inject this morning 100 nanograms of K562 cell lysate digest from Promega, commercial cell lysate. It's really what we use to do our QCs with, and it should provide a nice example of the capabilities of the dia-PASEF on the timsTOF. So, and I'll talk more as we go through later on about how this is working, and some of the how we can actually develop methods. But in the interest of time, because we actually want to get a data file acquired, I'm going to move straight on into acquiring an actual data raw data file itself. One of the first things I'm going to do before I actually start the acquisition, though, is actually to calibrate the mass spectrometer, right? Because obviously one of the things that we need to do is to, I would do typically the start of every, sample list, or maybe, once or twice a week, is to calibrate the master charge scale, but also the ion mobility scale, right? Because that's also a key part of the way that the TIMS process works. So calibration of the timsTOF is really very straightforward. What you'll see on the top of our captive spray source is this filter system here. So this is just a couple of filters here, which actually filter the lab air that we use to actually focus the spray onto the inlet to the mass spectrometer. So normally you have just an empty filter running here, just to, as I say, just to remove any contaminants from the gas flow through the system. But to calibrate, very straightforwardly, I'm actually just going to replace that filter with a filter that I have previously spiked with some calibration materials. And so if you look now at a real-time display, you can see there are now 3 distinct peaks here, 622, 922, and 1221. So these are our calibrant peaks. You can also see them in the mobility heat map too here, right? So this is these 3 distinct peaks here represent those calibrants. And so I'm going to use these calibrants to calibrate both the master charge scale and also the mobility axis. So this is very straightforward on the timsTOF. So literally I go to the calibration tab. And first of all, I'm going to calibrate the TOF, the master charge scale. So literally I just hit the calibrate button. And what you'll see is immediately, instantaneously, it will calibrate based on those 3 data points. I get a very good score, so I'm happy with that. So to accept that, I just hit the accept button, and now I've calibrated my mass scale. So then I need to go ahead and do the same thing for the ion mobility scale, right? So I'm going to calibrate the ion mobility axis the same way, using the same masses. So again, I just click the calibrate button, and I get a really good score. I press accept, and my mass spectrometer is calibrated. So then all I need to do is then swap those filters back over. So we now go over my standard running filter, and so basically the system is now all ready to go. So everything is calibrated. Those peaks will disappear very quickly. Now I've removed the filters. So now I've done that. All I need to do now is just come back to my my sample table. So I'm actually going to literally click on here, and here's my sample table. So you can see here in my sample table, I get my real-time feedback from my HPLC system for my nano-elute here. So it's showing me the pressures currently for the flow, the percentage B, what columns I may have attached, the column heater temperature. And of course, down below, my sample table, right? So I have a new line here. So I'm going to inject from this position in the auto sampler. As I said, I'm going to inject, so this is my sample ID. So basically, this is the Promega K562 digest, 100 nanograms on column. This is how much I'm injecting, where to save the data. And then most importantly, my HPLC method and my mass spec method, which we just looked at now. So once I have all those in place, which I do, I'm simply going to come over to here and press the start button, and I'm going to start that sequence. And what you'll see now is that the system will start to go through the whole process of obviously, setting the flow rates, setting the gradient, and picking up the sample and injecting it onto the column. So while that's going, maybe we can talk just a little bit more again about the setup, and then start to dig into more about the concepts of trapped ion mobility, and then also particularly focus on the data independent analysis. So what you'll see over there now is the LC will start to work. Why don't we move over there a little bit and have a look at a bit more detail. So so the nano-elute, so this is our own nano-LC system. This comes from the same group that also make the EvoSep1 system. Previously, they also worked on the EZ nano system, and so it comes from a long line of well-established and effective nano-LC systems. So you can see it comprises basically of a CTC PAL autosampler, so very robust, well-established autosampler. You can see now it's actually just now going to go ahead and draw sample from the sample vial. So in the sample carrier here, at the moment I'm using vials, but you can also use microtiter plates if you wish, if that's how you prefer to introduce your samples. That's also supported in the software. Or if you want, you can have a mixture of vials and microtiter plates. So once the system has picked up the sample, it just went to wash the needle, and now it's actually going to inject the sample onto our sample loop, which sits on this valve right here. Then the system will, using constant pressure, will then load that sample onto our separation column. Once that's complete, it will start the acquisition. And by the way, so the method I'm using here is effectively a gradient of 2% B to about 35% B over the course of about 7 minutes. So my total LC time will be 20 minutes. So it's going to be a 20-minute run, and there'll be a little bit of upfront time for the sample loading. But in total, as you can see, it's going to be a 20-minute LC method. So very quick, but hopefully it will give a good impression of how the sort of results you can attain from these, even this short gradient on the Tims-TOF Pro. So as I mentioned, so If you wished, of course, you could also load this onto a trap column first. So if you wanted to do a trap column loading experiment before moving it onto before pushing that onto the analytical column, that's also completely possible in the system. The trap column will just sit in this position on this valve here. But today we're not using a trap. We're just going to do direct injection onto the analytical column. And as I mentioned before, so the peptides will come through this transfer line here into our column toaster, which is our column heater, which is currently heating the column to about 50 degrees Celsius. And then and our column is inside the column heater there, and then into our captive spray source. So for those of you who are not familiar with captive spray, the idea of captive spray is, for one, there's no XYZ positioning, right? It's a plug and play device. So it's always going to put the emitter in exactly the right place. So there's no tuning or placement required there. So it's very, very simple to use. And the idea of captive spray is that we bring this gas flow around the outside of the emitter. And this gas flow helps to shape the spray. So you take your typical Taylor cone that you see from the end of, when you spray from the end of a narrow emitter, and we use that gas flow to actually shape and focus that spray onto the inlet to the other mass spectrometer. So it really maximizes the amount of ions we get into the system. At the same time, that gas flow continually sweeps the outside of the emitter, just helps to keep the emitter clean. And that gas flow is actually just, as I mentioned before, basically lab air that's poured by the vacuum of the mass spectrometer through the top of the source. And these filters are in place just to make sure that obviously we're to filter out any of the chemicals in the environment or any dust or the contaminants. So yeah, so as you can see, that's going to go along and inject and then run that gradient for us. So we'll let that carry on. I'll maybe jump to the acquisition, once it's got going, so you can sort of see the data acquisition, actually happening live. But while that's happening, why don't we jump back to the presentation, and we can talk a little bit more about some of the specifics here. So one of the things I mentioned is that one of the key features of the Tims-TOF Pro is this concept of trapped ion mobility, right? So this is a method of separating ions based on their collisional cross sections, right? Their ion mobilities, and the actual trapped ion mobility or Tims cell is actually located directly after the source, right? So what you'll see here in this slide here is the front of the instrument, right? A sort of schematic of that. And so you'll see this is our glass capillary. So this is the interface between the atmosphere and the first vacuum stage of the mass spectrometer. So our ions are going to come from our HPLC through this glass capillary, and then they are deflected with this plate into the first optics of the mass spectrometer. And all our neutrals are going to keep going and not enter the optics. So it just helps to keep the system cleaner as well, because this is completely orthogonal to the rest of the geometry of the system. So ions go through an entrance funnel here. This is an ion funnel, and then into our Tims analyzer. And so the concept of a Tims analyzer is basically we have a series of electrodes where we have an RF voltage to keep the ions contained. And at the same time, we have an increasing electric field as you go from the front to the end of the analyzer. And this electric field is effectively acting as a trap or a barrier for the ions. So this electric field is effectively trying to push the ions from right to left. At the same time, we have this constant gas flow coming through the system, pulled by the vacuum, which is going to push those ions into the electric field. And so as the ions as we accumulate, let's say 100 milliseconds worth of ions, this gas flow pushes those ions into the electric field. And the larger the collisional cross-section of the ion, the further that ion travels into the electric field before it reaches an equilibrium point where the force of the gas flow and the opposing force of the electric field are effectively in equilibrium, and the ion is trapped. Ions of smaller collisional cross section will not travel as far, so they are trapped at a different position. So now we've separated those ions based on their collisional cross sections. So this is what we call accumulate, and you'll see we have two of these TIMS analyzers in series. So basically we would accumulate some 100 milliseconds of ion current here, and then we would push those ions into the second TIMS analyzer, where again they separate based on their ion mobilities, their collisional cross sections. Once they've separated, we then ramp down the electric field. So we start to drop the electric field, and then ions will elute from the TIMS cell in order of their decreasing collisional cross section. At the same time, we accumulate on the first TIMS analyzer the next packet of ions. So this gives us a high resolution ion mobility separation, but also this very large amount of spatial focusing, right? So the ions elute in these very tight bands of ions, which enables us to get a significant sensitivity boost, and also do MSMS on these ions very, very quickly. And because we're always accumulating while we're separating ions, it gives us the ability to achieve virtually 100% duty cycle. So we're never throwing ions away, right? So we call this whole process parallel accumulation. So this is a concept that it's been around now for a little while. So this is, we first published on these concepts back in 2015, working with Professor Matthias Mann at the Max Planck Institute, and we came up with this concept we call PASEF, right? So which stands for parallel accumulation and serial fragmentation. It's how we do DDA. So we accumulate ions, we pass them through, we separate them, and we elute them, and we fragment each one as it comes out of the TIMS cell. And because of this focusing of the ions and the intensity in the sensitivity improvement enables us to do MSMS at rates of in excess of 100 MSMS in a second. So we can do very, very fast MSMS, very, very fast DDA experiments on this. So, and just to give you some feeling for what's possible from just doing DDA on the timsTOF system. This is results from an HEK cell line at two different concentrations and two different gradients. It's actually an in-house HEK digest, I should say. And so we ran this with a short gradient on just a 20 nanogram load, so 20 nanograms on column. And you can see here that we're able to identify around 4,500 protein groups, and very reproducibly across 8 replicates. So we get very high numbers of protein identifications from just a small sample load and a relatively short gradient. So of course the next question is, well, what if we push this out a bit more? How much can we? How can we push our IDs? And so down here you'll see this is now 200 nanograms loaded on column with a 70-minute gradient, and you can see now we're able to achieve in excess of 7,000 protein group identifications from this longer gradient and larger amount on column. So yeah, you can see that we can take advantage of that speed to run short gradients, the sensitivity of the TIMS process to be able to get high IDs even from relatively small amounts of protein digest on column. But we can also really take advantage of this sensitivity that we get, right? And also the sequencing speed, because the fact that we can sequence ions, fragment ions at over 100 MSMS per second means that we can really shorten down that gradient and still get very high numbers of protein identifications. So this is some results from effectively what is a 50 LCMS runs per day, right? So basically a 28-minute inject-to-inject LC method. And this was actually done on our nano-elute as you see it here. And And so you can see here we're able to identify well over 4,000 protein groups and 26,000 unique peptide sequences from this really very short method. This actually represents only a gradient time of about 17.8 minutes. So it's really very, very quick gradient, still achieving very high numbers of protein IDs. Okay, so but the being able to achieve very high ID numbers, and in particular being able to run large, these short gradients and still obtain very high depth of coverage, this is only possible, of course, if you have a very robust system, right? And so this is a slide that's I like to show because it shows some results from Roman Fisher's group, excuse me, in the Oxford University in the UK. Here's Raphael here next to the system. So basically, they ran in excess of 2,600 non-depleted plasma samples using 100 samples per day method. In this case, on the EvoSep 1 LC system. So this led to this equated to, with all the extra library and QC samples, achieving or acquiring in excess of 4,300 MS runs. And what's nice is that they didn't see any drop in performance over these samples. Other than changing the column, they didn't have to do any subsequent quick cleaning of the mass spectrometer. So and we're seeing this in timsTOF users labs, really across the world, that there's really very little maintenance that you have to do on the system, and it's proving to be really, really robust and really capable of running, and hence capable of running these larger sample cohorts without a lot of downtime for cleaning and maintenance. So we've spoken a lot about DDA, and in DDA and the timsTOF, because of the sequencing speed, means that we do have the chance to achieve and sequence more consistently the same ions across the data set, across your sample cohorts. But missingness is still an issue, right? Even for the timsTOF passive DDA experiment, missingness becomes a problem. By missingness, of course, I mean that as you inject sample to sample to sample, the fact that you don't fragment the same ions, the same peptides reproducibly across your sample cohort. And of course, if you don't fragment the same ions consistently across your data sets, across your sample batches, it means that you're not going to be able to quantify as many proteins, as many peptides, and hence as many proteins, across your cohort of samples. So and I think there's a reference that we pulled out here from MCP back in 2019, where they sort of highlighted this really quite nicely. This in particular was a TMT data set that they showed this, but it applies really to any sort of DDA type approach, right? Where as you go through and steadily increase the number of batches of samples that you analyze, then the number of percentage number of peptide missing values, right? So where you gets higher and higher, right? So you can see that after about 22 batches of samples, then there's more than almost 55% of the peptides are not present across all your samples. So it just means that you're not able to reliably quantitate all these proteins across these large batches of samples. So this is, of course, where DIA has a unique advantage, right? Because of course with DIA we don't have this stochastic precursor selection issue, because we're fragmenting everything, right? And we're not relying on an algorithm to pick peaks as they elute from the column. Also, if you're doing TMT, of course, you have to have this pooled sample to be able to match across batches and normalize across batches. So we don't need that. And obviously we can run this with a library-free type approach if needed. Excuse me here. And also, of course, there's this concept of retrospective analysis. Because you've acquired all the data in DIA, you can always go back and reinterrogate that data, because in theory you have MSMS of every peptide in the sample. So DIA is as is well established, has a lot of potential advantages over DDA, I mean in particular for label-free quantitative analysis. So the next question, of course, is how do we do DIA on the Tims-TOF Pro? So what I've pulled out here, and by the way, we call DIA on the timsTOF dia-PASEF. So what I've shown here is a heat map, right? So this is basically a plot of master charge along the x-axis, mobility on the y-axis, and what you see on any triptych digest type sample is two discrete areas of ions. So you have the singly charged data here, and then the multiply charged peptides in this area here. Right, so this is our background. This is stuff we don't care about, of course, and this is the data we care about. So if you think about a conventional DIA experiment, right, you're setting your quad window to a narrow mass range, and you're fragmenting, whatever masses come through the quad at that point. So this will, of course, in standard non-TIMS DIA methods, this will be the multiply charged peptides of interest, but also the singly charged background. So it means that all of your fragmentation, DIA fragmentation spectra are more complex because you've got, fragmentation or fragments from unwanted background ions to complicate the spectra. When we do dia-PASEF on the timsTOF, we're able to take advantage of the fact that we have separated out the singly charged from the multiply charged ions. And this time our windows are based in not just in terms of master charge, but also of mobility, right? CCS value. So you can see here, our windows are discretely placed only on the multiply charged portion of the data. So for example, we'd sample, for example, here, and then in the same accumulation, we would maybe move the quadrupole and an ion mobility window to here, and then down to here. So this whole process, we'd require 3 windows in just typically between 50 and 100 milliseconds, right? So then the process is really we just continue to then just offset our windows, right? So now we've offset all of our windows in terms of master charge and mobility for another 50 or 100 milliseconds worth of data. Repeat that again. So now we've offset again, right? Until we have covered the entire multiply charge range, right? And so to cover all of that range, takes us, somewhere between 0.7 and 1.3 seconds with this number of windows. So you can see that the cycle time is really fast, and so we can really, we can really keep up with, modern high-performance chromatography, shorter gradients, as we've spoken about already, and take advantage of the speed of the timsTOF in our DIA experiments. So this would be then the set of windows. Our windows, obviously, I said, contain master charge and mobility information, and we're to cover all of the multiply charge data of interest while completely filtering out effectively all the singly charged data. So that's basically the principle of how we do dia-PASEF on the timsTOF. So what does the data look like? So what you see here is so several different data sets here. So on the bottom left here, you can see what happens when we mix HeLa and yeast at the 2 different ratios. And you can see from this, using 100-minute gradient, we were able to quantify over 11,000 protein groups from this mixture, 200 nanograms of HeLa, and then between 15 and 45 nanograms of yeast. But not only do we get the very large number of protein identifications, we also get very nice quantitative, very accurate quantitative data. You can see that also plotted out here on this plot here. So you can see we're at we're quantifying over 8,600 human proteins and almost 3,000 proteins from yeast. So very high depth of coverage with nice accurate quantitative information. On the right-hand panel here, what we've done is to sort of show you the sort of numbers you can proteins we can identify from a typical human cell lysate. First of all, in the green here, by loading different amounts of this sample on column, right? So here you can see, in this case, loading 100 nanograms where we identify over 7,600 protein groups, all the way down to 10 nanograms where we're still identifying over 5,000 protein groups. So again, highlighting the sensitivity of the process. And then also the effect of changing gradient length, right? So here's effectively 60 samples per day, identifying 6,700 protein groups, even down to 200 samples per day, right? Which is effectively a 4.5-minute method. You can see we're still identifying over 5,000 protein groups. So, and then I also mentioned this data completeness, right? So let's look at, this is actually 18 injections of a complex cell lysate. And what you can see here is that we see really reproducible numbers of proteins identified. The red, if you see any red here, which you really can't, but this is from Spectronaut, and red would indicate where you have unique identifications. So basically, there's virtually no unique identifications in this data. So we're identifying the same proteins, but also the same peptides over and over again across our samples. So again, just sort of highlighting, the data completeness of dia-PASEF is really high. It means we're not seeing these unique identifications across our sample cohorts. It's really reproducible. So I guess I just wanted to just finish on our last couple of points. So as Vic mentioned, in a previous live from the lab we did, we showed how we could do a DDA experiment in real time, and also have this real-time database search with our new PASEF search engine, which searches data in real time. Every time the system produces an MSMS spectrum, it's searched by our PASEF search engine, so that by the time the acquisition is complete, you have your search results done for you. And we can this is something you can go back and look at on YouTube, actually, to look at this, or our website to see that particular demonstration if you're interested in seeing more on that. So as far as DIA is concerned, so we're actually going to be adding dia-PASEF data processing to our PASEF search engine in the next couple of months. So look out for that. If you already have a PASEF search engine in your lab, we'll be able to support dia-PASEF data very soon. But also I wanted to highlight here that virtually every commercial or popular software package, proteomics software package, supports timsTOF data natively. So here you can see all the search engines that support the PASEF DDA result data. But obviously of all importance today for DIA data, you can see that we can use Spectronaut, Diane, Peaks, MaxQuant, Skyline, all have timsTOF data supported in their DIA workflows. So you're really quite covered in, you have quite a lot of choice as to what data analysis package you want to use for dia-PASEF data. Okay, so finally, just a quick update on our timsTOF products. So many of you may remember the original timsTOF Pro launched back in 2017. So last year, over the summer, we launched an upgraded version of the system, the timsTOF Pro 2, which is, by the way, you can upgrade a timsTOF Pro to a timsTOF Pro 2 if you wish. But at the same time, we also launched a new timsTOF we call the timsTOF SCP, which is really designed and developed for ultra high sensitivity proteomics. Any sample you have where you're really limited on the amount of sample you have, right? So single cell proteomics, immunopeptidomics, etc. But also, we also have the Flex series of timsTOFs, which in addition to the ESI capabilities we're looking at today, also have the addition of a MALDI source. So we can do, for example, tissue imaging workflows on this, including a newer version which has an additional laser for the ultimate MALDI sensitivity for things that are hard to ionize. So there's lots of capability here in the timsTOF, both from a electrospray and also a MALDI point of view. Okay, so that was pretty much what I wanted to show you here on the slides here. So let's go back, and actually what you'll see is while I've been talking away here, the acquisition is actually completed. You'll see it says acquisition done, so the acquisition is finished. So what I'm going to do now is I'm going to actually just copy that raw data file that we just acquired, and I'm going to copy it to our data processing station here. So let's just grab my newest data file. I'm literally in real time here, just going to copy that into my processing computer very quickly here. And then what I'm going to do is I'm going to search this data file on our processing computer using the DINN or DIAN software, right? So I'm literally now going to pull up that data file. So that's the data file that we just acquired this afternoon here. So there's a data file there, and I'm going to search it against a spectral library. And this spectral library we created here in-house, which is basically just multiple acquisitions of this K562 cell lysate, and creating a spectral library from that. We added a FASTA file here for the human from UniPro. So I basically got my parameters set up here. So basically all I need to do now is just literally hit the run button, and then you'll see that the system will now start to, the software DINN will now start to process this data. And you'll get a feeling now for just how quick this is, right? So as far as settings for this, by the way, I'm really just using very standard settings, nothing particularly complicated or different here. We're pretty much using the standard parameters for the dia-PASEF software. I'll also show you this similar data file processed in the Spectronaut software, and just to give you some contrast in how these softwares look, how they work, how you interact with them, and the sort of results that they can achieve. So what you'll see now is actually basically the run is basically almost complete. So it's just going to take just a few moments. So actually, why don't we just, while we're waiting, actually, so what you'll see is that DINN is very, very quick, right? So it acquires data, it processes data very, very fast, and it really does a great job of in data in terms of spectral identifications, protein identifications, and quantitation. And the resulting output, as we'll see in a little bit, is basically a set of tables containing all of the peptides and proteins identified. So you'll see here actually that it's actually finished that process. So now let's go back and look here at the results here. So it produces this PDF output here. And I'll just scroll through this because it's not very exciting, because of course we're only acquiring a single data file here. So a lot of these views are not particularly useful. But what I do want to show you here is number of peptides we're identifying here. So so over 33,000 peptides identified from this 12-minute gradient, and well over 5,000 protein identifications. So with this very, very short gradients, this very fast method, we've still achieved over 5,000 protein groups. So I should also show you here that DIAN also produces all these very useful tables here, right? So you have an output table of all the protein groups, the peptides, and other information about the data processing. So if I move now to Spectronaut, what you'll see is basically the same data acquisition processed in Spectronaut. And here you can see identifying over 5,000 protein groups and 28,000 peptides. So the results are really quite similar. Yeah. What Spectronaut does give you, of course, this is a commercial software package as opposed to DIAN, which is something that you can download and use, license free. Is Spectronaut gives you this, a sort of a more graphical user interface that allows you to interact with the results in Spectronaut and sort of see some of this information a bit more clearly. So, for example, here you can see that same plot of the eye mobility, right? So here's the singly charged data, here's the multiply charged data, and you can see it also superimposes our DIA windows onto the data. So you can see that we've sampled the data nicely in this case. And also, so Spectronaut also allows you to dig and actually look at some of these, these identifications that it's come up with, and to be able to see, extracted ion chromatograms, protein coverage maps, etc. for your identifications. Something that Diane doesn't freely allow, and is not enabled in Diane, right? It's a bit more simplistic user interface. The results are still great, but it lacks this sort of ability to dig down into your data within the software itself that Spectronaut gives you. So yeah, it's a little bit more interactive and allows you to sort of get a more visual inspection of your database search results. Yeah. So yeah. So really, I guess as if you wanted to contrast the two softwares, it's really the fact that Spectronaut is a supported, more commercially supported software, but of course has a cost behind it, whereas Diane produces as good or better IDs and quantitative results, but without this user interface that you see here. Okay, so I know we're getting a shorter time here, so I wonder now if it's a good chance to maybe see if anybody has any questions that we can answer.
Yeah, hey Matt, thanks for that. There's actually a bunch of questions in, and I think we can try and just get a couple of easy ones out the way. There was a question of robustness, and about what routine maintenance might be required. So maybe you could just speak to that a little bit on the instrument. And
yeah,
it's
sure.
good that you've got the instrument control. There was also a request, I think somebody texted me saying it would be great to see the data actually being acquired. So I don't know if you want to inject another sample even, and then we can see some peptides coming off the column before the end of the actual discussion.
I can. Let's quickly add another run here, and set that going. Hopefully we'll be able to see something acquiring before the end of the session. Yeah. So okay, cool. So we'll let that go.
But yeah, we got some other good questions here. Question about throughput. What's the possible throughput on the Tims-TOF Pro 2 using the dia-PASEF?
Yeah, absolutely. So yeah, I think we sort of alluded to this a bit, right? So if you have an LC system like the EvoSep, you can really run at these very high these very short gradients, right? So these so-called 200 or 300 samples per day methods that they have allow you to acquire data at the over just a 5-minute gradient. And but of course you can push that all the way out to these longer gradients if you really want to see the maximum depth of coverage, like I had in the example where we had the human and yeast mixed proteome experiment, where we had those we saw over 11,000 quantified proteins from a 100-minute gradient. So I guess it really depends on what sort of depth of coverage versus how many samples you have to analyze.
And so what would you say is, I mean, if you had to say about ID rates, if you were going to do DDA versus DIA, how much more IDs would you get under comparable conditions, do you think?
Yeah, okay. So I guess if you look at just the sample we ran today, right? So there's 100 nanograms of K562, where we're identifying about 5,000 proteins with DINN. If you did the same thing in DDA mode, I'd expect to see probably around about 3,000 protein groups, 3,500 protein groups. So you can see that you do get significantly more depth with dia-PASEF compared to DDA, even on the timsTOF.
Right, brilliant. There's a question came about, do you use an external or an internal calibrant during the acquisition to maintain the mass accuracy? So
that's a great question.
What's
possible? So at the start I went through the calibration routine, and that's pretty much all we do for a batch of samples, right? So if I'm running samples over the weekend, then I'll do that same calibration process, and that's all I need to do. So both the flight tube and the high voltage electronics in the timsTOF are maintained at a constant 25 degrees Celsius. And so because of that, we see very little drift of the on the system. So that single calibration that I did, will last you for several days before you need to do that again. So
yep. Great.
I also realized we didn't actually get around to answering the question about routine maintenance either. So yes, the only two things you have to routinely look after is the captive spray source itself, because of course this is where we're spraying our samples, and so this is the first thing that will get dirty. So this is a very simple thing to clean. We just remove this front of the source here, and we just rinse that with some, formic acid, isopropanol, and then dry it with nitrogen and put it back in. It's a 5-minute process. After that, probably every, 6 months or so, maybe sometimes a year, depending on your throughput, then that glass capillary, which is the interface between atmosphere and vacuum, that we'll need to take out and clean. Typically, the system comes with 2, so you can, remove one, put the clean one in, and you can back them and running in like 2 or 3 hours. So it's really quite quick.
Fantastic. Quick question on, do you have a recommendation, Diane versus Max Quant? What are your views there?
Versus Max Quant.
Yeah.
So we tend to use Diane at the moment, most frequently, or Spectronaut, here at least. I know Max Quant was only released, I guess, middle last year for be able to process DIA data. At the moment, we've found that the peptides in Max Quant are probably a little, it's not identifying quite as many peptides as both Diane and Spectronaut, in our experience. It maybe takes a little bit longer to process the data. I think often it's more a case, an idea of what you feel most comfortable using, right?
Fantastic. Okay. Is there an easy way to show the process for generating the dia-PASEF window table? While you're running, I wasn't sure.
Yeah, while I'm running, it's a little bit difficult, but I can at least show you.
To that one?
Yeah, we can come back to that one. Absolutely.
I think it'd be good to take a look at that in a minute.
Yes, of course.
Question on how sensitive is the system maybe to residual detergents? I mean, with this singly charged stuff versus other mass specs. Yeah.
I think as with any mass spectrometer, right? We always try to avoid as much as possible introducing detergents into the system. So I'd say it's probably, as robust to detergents as most other systems. It's always something that we would try to avoid introducing as much as possible.
Yep. Okay. I'm just trying. There's a slew of questions now suddenly descended on me, and they keep changing the order in which they're showing up. So apologies for that, but I guess that's good.
You'll see this in real time, actually. So by the way, the system's still loading the sample, but what you'll see here in real time is these ions here are the singly charged data that we saw earlier, and you can just start to see some peptides starting to elute here, right? So here's some of the peptides, and you can see they're well separated from the singly charged data here. This is only showing MS1 data. I can change it to MS2 data, but the system is really quite fast, and it probably doesn't really show it to its, to what you expect to see. So I think this is probably a better view of what's happening. So every time you're seeing here is a new MS1 spectrum after having run through all of those windows.
Yep. Brilliant. There's a question about higher charge states than 2 and 3. I take it there's no restriction in looking for them, and
not at all, right? So in fact, if we just come back quickly to that slide where we have the we showed the that heat map, right, where we set the windows. So these are all the multiply charged ions, right? So this darker patch here will be most of the doubly and triply charged ions, which of course we see most in tryptophan digests. You'll see some other ions here, so that those higher charge states will end up just having lower mobilities here, right? Lower what we call 1/k0s. So they will fall a bit further down here, but there's still something that the windows will happily pick up. Or of course you can adjust the windows if you want to focus on those ions in particular.
Right, brilliant. There's a question on setting up the DI methods. We'll come back to that. Is PASEF similar to Proteome Discover or Peaks?
Yeah, so PASEF, so I didn't really spend a lot of time talking about that, but so PASEF is actually based on the IP2 search engine that came from John Yates's group at the Scripps Institute. So they spun that company off from Scripps, and actually Bruker purchased that company, I guess a couple of years ago now. And so yeah, so it's based on that search technology, but by using graphics card processing, we're able to really speed up the database search, such that, as we mentioned, it's literally doing the searching each spectrum on the fly. Even when we're acquiring data at over 100 MSMS per second, because of this high number of cores in the graphics cards, we're able to keep up with that with that data acquisition rate and search all those MSMS spectra in real time, such that, as I mentioned, once the acquisition is completed, your database search is complete as well. So no having to move the data to a search engine, wait for the search engine to process the data. You get that database search result straight away.
Brilliant. Just a question: is there a library in the case of this DIA data, or do you do it library free?
Yeah, fantastic. So I sort of didn't spend much time on that. So in this case, we did a library-based search. So what we did was, because we use K562 as our standard QC anyway, we have lots of DDA data on this. So I think this was about 20 DDA files, which we used to create a library, and that's what we're searching against. Obviously, if you want to go even into more depth, right, then the workflow would be to do to fractionate your sample, typically a pooled sample of your sample cohorts, fractionate that into anything from 8 to 24 fractions, acquire DDA in those, and use that as your library. But as you mentioned, the alternative workflow, which is now becoming quite established, and is this library-free approach, right, where we're not having to supply this library, and it's been effectively doing this in silico library production. And this is now very competitive, certainly with DDA, and even now starting to become more competitive with even library-based approaches in DIA.
Brilliant. Okay, a couple more things then. I think where was it? There was a good question here about setting it up, but I can't find it now. So yeah, we talked about the spectral library. Does the dia-PASEF fragmentation method start with the higher master charge values and go backwards to lower mass? So it might be good just to say again how in the DIA the ions are fed from the TIMS, and then what it's doing in terms of.
Great question again. Yeah, absolutely. So again, so this is what our data looks like to the system, right? So basically, the ions elute, right, from the highest mobility, the ions of largest collisional cross section elute first, and the ions of smallest collisional cross section elute last, right? So when we set our windows accordingly, right? So we set them to the highest part of the mass range, and then like the mid and the last, and then just continually step that across, right? So so yeah, I guess we're not necessarily acquiring the highest or largest mass first. We're just covering the entire mass range over that 1 second cycle or whatever it may be.
Yeah. Is there any difference between doing library free and the library searched ones for peptide detection reproducibility, or do you feel is that the same? Or does it not matter?
In my experience, it's been really pretty similar between the two in terms of the reproducibility. I haven't seen any major differences there. But it is still the case that a good library will still outperform library free in most cases.
Okay. There was a question here about detecting if the signal. How do you know if there's a change in the signal or whatever? If you need to do something with the emitter or the column.
Yeah. Okay, that's a great question. So yeah, so you tend to see that in spray stability. or just performance of your QC. That's the two metrics that we only use to spray stability. I mean, just like the the baseline spray from the system.
Okay, and then I know the other question I was trying to get to. So you have this heat map that we're seeing here. Can you explain how you define the data independent window setup, both in mobility and master charge?
So why don't we do that, right? So
real run and like a DDA survey run initially. I think that's what they're getting at.
Yes, exactly. So, you know what? Because I'm going to stop this run. We saw sort of the basics of how it's acquiring data, right? So let's just stop that. And let's move on to actually look at the editor itself, right? So if I go to my MSMS settings here, you can actually see in this window the actual windows we have. Now, if you want to modify this or set it up from the beginning, I just go to my window editor here. And then the software will either load in the last data file or previous data file, or you can open a data file here, and maybe basically a DDA data file, right? And or a DIA data file, it doesn't actually matter. And the system will recreate that heat map, and you can see the current window set up across the data. But let's clear that out the way. So again, obviously we want to put our windows across this part of the data, right? So what you see is this polygon. So first of all, we can actually position this polygon by grabbing the edges here. Alternatively, so I can just move that up, right, just to place it. And then what we can also do though is that if that's not enough points, right, if you want to be a bit more specific, I can just double click on here, add a new point or a couple of new points, and then I can just position this whole set of windows, right, exactly where I want them to cover my area of interest, right? So I'm just going to put this polygon over where basically all my data sits, right? So my multiply charge data. And then over here, and all I'm going to do is just tell it what the mass width for my windows is going to be, any overlap I want to put in, and then calculate windows, and it will actually develop those windows and put those windows in across my data, right? So it's really very simple. You basically just define the area you want to have the windows, you define how large you want the windows to be, and you just put them in. So for example, if I wanted to use, like more steps or narrow windows, say for example, so let's say I wanted to use, I don't know, 20 Dalton windows, then I can just put that in and hit calculate windows, and it will change that, right? Or if I want to put less windows in, or narrow or wider windows, it'll do that for me. So you can tailor this to exactly how you want it. Maybe you want to make 2 passes across the multiple charge data. Now I'm doing, I'll split each of my mobility windows into 2 separate windows. Yeah, minimize my cycle time, and I just apply these windows to my method. So that's basically it. So it's really quite simple to use, but really quite a powerful editor.
All right. No, that's great stuff, Matt. Well, look, we're out of time.
Yep.
I don't know that I've gotten to every question, so if I missed you, I do apologize. I've made a valiant attempt. Please email me if there's something burning.
Yeah, I think actually, Vic, we'll have a record of all the questions and who asked them, so we can respond to you individually if we didn't get a chance to answer your question.
If you didn't, send me a note and we'll come back to you.
Exactly.
Victor.Percy@Bruker.com. So we're out of time. I must thank you again, Matt, for a fantastic job today. You've been getting some glowing comments in the questions as well, so I just want to relay those to you. And very much appreciated to spend an hour with you.
Thank you, everybody. I appreciate everybody's taking their time of their day to spend some time with us and look at the workflow.
Perfect. So we should be able to get this recording up on the website soon, and those who've missed it should be able to come and look another time.
Yeah, I think also the system will send you a download link for the recording as well. So yeah, Perfect. If you had to bail out early, then that will still be available.
All right. Well, I think we've come to the end of the road time-wise. I'd like to thank everybody for sticking with us. There's still almost everybody still on the thing here. And so thanks for your time. look out for the next one. Maybe the next will be on PRM or another topic close to your heart. So keep an eye out for these invites as they come through. Thanks, Matt. Thanks, everybody.
Okay. Thank you, everybody.